specific set of conditions. Hi, my name is Scott Simpson, and today we'll be talking about standard reduction potentials. So standard reduction potentials are often used to calculate the potential that you will get from developing a galvanic cell. In terms of the standard reduction potential, it's under a specific set of conditions in which you measure this. So what we're going to do today is talk about what is the standard reduction potential, what are the conditions for it, and how to utilize it to calculate the potential or the electromotive force of a cell under standard conditions. So these standard reduction potentials, or they're sometimes given the symbol E naught. It's the potential at 25 degrees C, 1 atmosphere of pressure, and where everything is at 1 mole. Molar concentration for reactants and products. Hence, that little naught symbol up there, that lets you know that it's under standard conditions. The standard potential or electromotive force for a cell, in this case, it would be E naught sub cell. So if we're talking about a battery that we've built, it's given by E naught cell is equal to E naught of your cathode plus E naught anode. All right, now you may be saying, Dr. Simpson, wait, when I look at my book, this is actually a subtraction here. It's not a plus. I take a different methodology, which I'll explain in a little bit on why I like to utilize this equation. So there are 2 techniques you can go about to figure this out. With my technique, you utilize this. If you want to go with negatives, we'll talk about that in a little bit. Okay, so let's talk about standard reduction potentials for cells. Reduction potentials of cells. And half reactions. So the first thing is you can find a lot of these half reactions or the standard reduction potential for those half reactions in tables in your book. So a lot of times they have appendices. So each half reaction has an E naught. Okay, and most you can find, like I said, in your appendix. As an example, let's look at it. So, example, if we look up the one for silver, so we have Ag plus an electron, goes to Ag solid. And you look up the standard reduction potential for this guy, it ends up being plus 0.80 volts. Okay. So this shows the reduction reaction or half reaction that we're talking about, and this is the potential you get. Now, this potential is in comparison to a very specific electrode, a very specific reduction reaction. And this is actually known as the standard hydrogen electrode. Standard being one that everything's compared to, hydrogen electrode, looking at the reduction of hydrogen. So this is known sometimes as the She electrode, but we're going to make a point to talk about that. So all E naughts that you look up in the table, they're in reference to the standard hydrogen electrode. sometimes called the sheet. Okay, so what is this reduction? It's just the reduction of hydrogen. So we have two H pluses. We add in an electron, and from this, what we get is we get molecular hydrogen, H2 gas. Now, since this is the reduction potential that everything is compared to, this will have an E naught of 0 volts, and it is exactly 0 volts that it has. So the way that you find standard reduction potentials is you take a cell with the standard hydrogen electrode on one side, and whatever other reduction that you want to look at. And from that, that's how you get these E naught values. So there's some small things to keep in mind when looking at these standard reduction potentials for half reactions. So the big thing, which seems kind of strange and counterintuitive, is E naught does not change if you have to multiply the half reaction by coefficients. So even if you multiply coefficients. So the reduction potential does drop over time because the reaction's occurring. But in this case, if you double or triple your half reaction, E naught does not change. So for example, if we take our half reaction that's over here and we double it, and we get 2Ag solid, the E naught, or the standard reduction potential, will not double. It stays the same, positive 0.80 volts. Which seems a little strange because in all other instances, when we did this, this would end up doubling, like we were considering enthalpies or Gibbs energies. But in the case of E naught, you just conserve that value. So keep that in mind when balancing half reactions. Okay, so earlier I said it was the cell potential, the standard cell potential was E cathode plus E anode, but when you look at most books, it's E cathode minus E anode. The reason for that is if you switch the direction of this reaction, you change the sign of E naught. So another important point, the sign of E naught changes. If you change the direction. So if we were to take silver and we were to oxidize it, instead of reducing it, the E naught would be plus, changing sign would be negative 0.80 volts. Some people elect to not do it this way. They just do E cathode minus E anode. I think this is more intuitive, so that's the way that I do it. Okay, so let's look at an example where we use standard reduction potentials and we calculate E naught for the cell or some battery that we built. So example, calculate E naught, or gotta watch out for that white spot there. Let's look at a zinc copper cell. In a zinc copper cell, what we first have to do is look up the standard reduction potentials of these guys to figure out what's going to be oxidized and what's going to be reduced. So we need to look up those values. Look up those values from our appendices. So we got, if we're considering the standard reduction potential, zinc plus 2 electrons goes to zinc solid. The E naught for this reaction, when we look it up, should be negative 0.76 volts. And then for copper, plus 2 electrons gets us to copper solid. That standard reduction potential is positive 0.34 volts. Okay, so looking at these standard reduction potentials, we have to figure out which thing is going to be oxidized, which thing is going to be reduced. Looking at this, you can see that this standard reduction potential is more negative for zinc than it is for copper. So what that means is this system actually doesn't want to be reduced, it wants to be oxidized. So we need to flip it. So, let's see if I can get this thing to go. A little bit better. So in that case, we need to flip this top reaction. So we're going to have zinc solid goes to zinc 2 plus 2 electrons. Now that we flipped it, our E naught becomes positive 0.76 volts. Okay, our copper reaction is just going to stay the same. Ends up going to copper solid, and our standard reduction potential doesn't change, stays at positive 3.7. Oops, 4.34 volts. Now we're going to combine these two half reactions together. That's going to get us the overall change of our cell. So the electrons cancel out. And finally, we're left over with zinc solid plus copper 2 plus. And no, I'm keeping off the standard reduction potentials. I'm sorry, I'm keeping off the physical states of these guys. I don't know if you can see that, so let's turn that up a little bit. That might be a little bit better. Goes to zinc 2 plus and our solid copper. And now all we need to do is just add these standard reduction potentials together. When we do that, we're going to get a value, E cell, equal to those two things added together, so 1.10 volts. Okay. So you can utilize this methodology to calculate standard reduction potentials and figure out what will the total E naught of the cell be. So keep in mind, big things. If you change the direction, you change the sign of the E naught. If you multiply these guys by coefficients, it does not change the value of E naught. So keep that in mind. So I'd like to thank you for listening. If you have any questions or comments, please leave them below. Thank you.